Oh, hi there. I didn't see you there. What up, Chem Gang? It's Jeremy again. And we're back. We're going to be talking today about relative atomic mass. Alright, guys, let's take a few periodic table of elements, different ones, and let's look at them. Now, what do you see? The atomic number is always this whole number. And what does the atomic number represent? Always represents the number of protons that you will find inside of the nucleus. So it's always 1 for hydrogen, 2 for helium, 6 for carbon, whatever the case, it's always a whole number. However, the thing about it is when you look at different periodic table of elements, the mass number is slightly different. For some, they give you this whole number, which we've come to expect because as we know, the mass number is always equal to the number of protons plus the number of neutrons. So for example, in the case of carbon, which has 6 protons and 6 neutrons, we expect to see a mass number of 12. And some periodic table of elements give us that mass number of 12 flat. But then we look at another periodic table of elements and we see something a little bit different. Welcome to the relative atomic mass. Now, firstly, the key word here to remember is that word relative. And anytime you hear a person talking about relative, you hear them talking about it like this. Oh, well, relative to that, this thing is that, or this thing is that. This thing is tall, or this thing is short, or whatever the case may be. Let me give you an example. I'm 5'6", 150 pounds. I'm really not a huge guy. But when I stand next to my friend who's 5'6", 130 pounds, persons will always say, oh gosh, well Jeremy, oh, compared to him, you're so fat, or relative to him, you're a big guy. So that's how atoms are, the masses of atoms are really quantified as relative to one another. And the reason for that is because atoms are so small that it becomes a real challenge in a day-to-day, everyday scenario to quantify them. Okay, let's try to quantify one atom right now, like hydrogen, like 0.00000000000000000. You get the point. Atoms are extremely small in mass and in size, and therefore to quantify them, it makes more sense to develop a scale whereby you give the masses relative to one another. On that scale, we take carbon 12 really and truly to be the standard of measurements for it, and everything else is relative to that. So basically nitrogen is 14, and that's relative to carbon, which is 12. Hydrogen is 1, and all of that is relative to carbon, which we talk about being 12 atomic mass units in terms of mass. Now, back to these decimals in the mass numbers of these elements or some of these periodic table of elements. Now, the reason why you do not see a whole number on some periodic table of elements is because the actual relative atomic mass of the atoms of the element are given. Now, what do we mean by that? If I give you a cylinder of hydrogen, we assume that there's only one type of hydrogen inside of this cylinder, being the hydrogen that we know. We assume that the hydrogen that we have inside of the cylinder has 1 proton, no neutrons. That's what we assume, right? But our assumption is actually very wrong. Plot twist! No, I'm very serious. Anytime that we're given this pure substance or pure element, the number one thing that we assume is that all of the atoms in it are the same. No, that's not actually true. There are other types of atoms that make up the same element, or there are different types of atoms that make up the same element. Let's look at the same hydrogen. See, in hydrogen, there's a type of hydrogen atom known as protium. Now in protium, there's 1 proton, but there are no neutrons, so it has a mass number of 1. Deuterium has the same amount of protons in it as protium. It has 1 proton. However, it also has 1 neutron, and therefore the mass number of deuterium is different from the mass number of protium. That is a phenomenon that we know as isotopes. Now, when calculating the relative atomic mass of any element, you have to consider the abundances of these different isotopes or different atoms of the same element. Because remember, we said that they all offer some sort of mass to the overall mass. So therefore, we have to consider the kind of abundance that they're actually in. For example, we have protium, which is found in nature 99.9% of the times that you find a wild hydrogen. Yes, guys, Pokemon reference. You find a hydrogen, you're going to find 99.9% of the time it is protium. Now, the other 0.1% of the time, you will find deuterium. It's as simple as that. So let's look at our example here. If I had 100 grams of elemental hydrogen, I expect that 99.9% of it would be protium, just the same way as it is in nature, and then 0.1% of that 100 grams would be deuterium. So therefore, the total relative atomic mass, I'd have to take 99.9, multiply it by 1 for the mass number of protium, and then I'd have to take 0.1% and multiply it by 2, which is the relative atomic mass, which is the mass number, of deuterium. That would give me a total of 100.1. Now, the relative atomic mass is described as the average mass number of an atom inside of an element, taking into consideration all the types of elements, all the types of isotopes in their relative abundance. So therefore, I can't just stop at leaving the total relative atomic mass as 100.1 grams. I now need to find out what the average is. And I said I had 100 grams before, so therefore I would take 100.1 and divide it by 100. That would give me 1.001 AMU, atomic mass units, which is not far off from this one, 1.008 atomic mass units, which I would have taken off of a periodic table of elements that I found on Google. Now, if I wanted to circumvent all of that, if I had 100 grams of elemental hydrogen, find the total, then do the average, I could simply work with percentages from the jump. Because I know that my protium has 99.9% of abundance, and I multiply that by the molar number of protium, which is 1, and then I know that the abundance of deuterium is 0.1%. I multiply that by the molar mass of the mass number of deuterium, which is 2, and I divide by 100, right? The percentage, and again I will end up with 1.001 AMU. Guys, I hope you guys have got that. You guys can take a try with this one. This is gallium. It's an element found right under phosphorus. And you guys can take a shot at it. And you have gallium 69. You guys have your abundance. Sorry, it's actually found under aluminum. You guys have your mass number, your abundance of gallium 69, your mass number of gallium 71, and your abundance of gallium 71. So you guys can give that a try and check me back here at the Chemistry Chem Gang, and let's do this.